Welcome back. Today's goal of this lecture. In my previous video I had seen, today I will see reducible and irreducible polynomial. What is reducible and irreducible polynomial? Consider DB an integral domain. Then a polynomial from dx which is neither zero polynomial nor unit in dx, where d be the integral domain, is said to be irreducible over d whenever fx is expressed as product of two polynomial, means fx equal to gx times hx, with the condition where gx hx in dx, with the condition either gx or hx is a unit in dx, where d be an integral domain. This is the idea of irreducible polynomial, and when a non-zero non-unit element of dx that is not irreducible over d, then this is called reducible over d. I hope my all viewers have understood what is the reducible and irreducible polynomial. When the polynomial is belongs to in integral domain, when polynomial belongs to in field, then definition would be other. When polynomial belongs to integral domain, then what would be the definition? Okay. If we write as for example fx equal to 2x square plus 4, obviously this is irreducible over q, because 2x square plus 4 means 2 times x square plus 2, which is written as gx times hx. And notice gx equal to 2 is a unit in q. So, obviously, this is irreducible over q. But over the field, over z, in zx, this is reducible. Why reducible? Because 2 times x square plus 2. Here, neither 2 nor x square plus 2 be unit in zx. So if we consider fx equal to 2x square plus 4, this is irreducible over q but reducible over zx. That means reducible and irreducible depends on the domain. Okay. Same polynomial, but this is irreducible over q, not reducible over zx. Similarly, this is irreducible over not only q, this is irreducible over real number, but this is reducible not only zx, this is reducible also complex number. Why? Because 2 times x square plus 2, we can split this as 2 times x plus square root of 2i times x minus square root of 2i. Because for a field, there exists extra condition if any polynomial fx in fx is irreducible if fx cannot be expressed as product of two polynomial of lower degree. Since here fx is expressed as product of of these two polynomials of lower degree, so fx is reducible over complex number. Similarly, if we write fx equal to x square minus 3, this is irreducible over q, but this is reducible over real number because we can split this as. So fx is reducible over real number. I hope my all viewers have understood this is okay. OL. Fx equal to xa cube plus x square plus x plus 1. We can factor this polynomial such type x square times x plus 1 plus 1 times x plus 1. Therefore, this is means fx equal to x square plus 1 times x plus 1. Which is actually we can write fx equal to a6 times gx, where obviously a6 means x square plus 1 and gx means x plus 1. Then neither a6 nor gx is a unit in qx or rx or zx. So this is not be irreducible polynomial in qx or rx or zx. Okay? Because we can factor this part in lower degree polynomial also. Okay? OL. Our next theorem to check reducible or irreducible, I will see reducible or irreducible for the second or and third degree polynomial. The theorem is consider f be a field and consider polynomial be the member of fx, and here this theorem is applicable for the degree of fx equal to 2 or 3. Then fx is reducible over the f if f has 0 in this field. That means if fa equal to 0 for any a, then we can tell fx is reducible over f, and if fa not equal to 0 for all a belongs to zp, then we can tell fx is irreducible over zp. As for example, consider fx equal to x square plus 1. Notice here the polynomial of degree 2. So we can apply this theorem, and we have here the question, is the polynomial reducible or irreducible over the field Z5? Z5 means obviously the field contains 0, 1, 2, 3, 4. Notice here f0 equal to 1, f1 equal to 2, f2 equal to 5, and in Z5 this is obviously congruent to 0, f3 equal to 10, and in Z5 this is congruent to 0, f4 equal to 17, and in Z5 this is congruent to 3. That means 2 and 3 be the root of this polynomial, and since I have got 0 in this field of this polynomial, so obviously this fx is reducible over Z5. I hope my all viewers have understood this theorem clearly, and use of this theorem if we consider same polynomial but in different field. Consider same polynomial over the field Z3, then obviously f of 0 equal to 1, f of 3 equal to 10, and mod 3 this value is equal to 1, and f of 1 equal to 2. So, fx equal to x square plus 1, this polynomial is irreducible over Z3. I hope my all viewers have understood, but this polynomial is reducible over Z5. That means reducible and irreducibility, this is actually depends on over the field, okay, OL. Second theorem, actually this is not theorem, this is be the property, and this property actually very important. The property is let fx be in zx, and if fx is reducible over the rational number, then that imply always this is reducible over integer. Also, if fx is irreducible over integer, then that imply this is irreducible over rational number. Next test is mod p irreducible test. This test also very important for reducible and irreducibility test. The test is let p be a prime number and suppose that fx in zx with the condition degree of fx greater than equal to 1, and let f bar x be the polynomial in zpx obtained from fx by reducing all coefficient of fx by in modulo p, and if f bar x be the irreducible over zp and degree of f bar x, these two condition, this condition is very important, degree of f bar x always equal to degree of fx, then we can tell fx is irreducible over q. If f bar, which is reducing all coefficient of fx by modulo p, but irreducible when first condition degree would be same, second condition if over zp f bar is irreducible, then we can tell fx is irreducible over. Well, consider fx equal to 21x cube minus 3x square plus 2x plus 8. Is fx is irreducible over rational number? For this, at first consider the prime p equal to 2. Then obviously f bar x after reducing this would be x cube plus x square, and since f bar equal to f, degree of f bar is equal to degree of f, so we can apply mod p test. Notice f bar 0 equal to 0 and f bar 1 equal to 2, which is congruent to 0 in mod 2, but in mod 2 test does not apply, does not tell about the reducibility, it only tell about the irreducibility. So we cannot get any conclusion by the prime p equal to 2. Here I have got one printing mistake. Here not would be x, here would be x squared. But at f prime 0 and f prime 1, this value would be same. Because x square and x, after putting 0 and 1, this value would be same. Next, consider the prime p equal to 3. Then f bar x would be 2x plus 2. Notice here degree of fx not equal to degree of f bar x. Since these two degree both not equal, so we cannot apply mod p test also. Next, consider p equal to 5. And at p equal to 5, then f bar x would be x cube plus 2x square plus 2x plus 3. Notice here degree of f bar equal to degree of f. So obviously we can apply the mod p test. Second condition, notice f bar 0 which is equal to 3, f bar 1 which would be equal to 8, and in mod 5 this is congruent to 3, f bar 2 this would be 8 plus 4 plus 3 means 16 plus 7, which is equal to 23, and in mod 5 this would be congruent to 3. F bar 3 would be 7 to 1, and in mod 3 this would be equal to 1. Similarly, F bar 4 would be not equal to 0. Since it has no 0 in mod 5, so obviously for this prime we can tell the function fx is irreducible over q. And we all of us know, if f is irreducible over q, then that implies this is irreducible over z also. Today I will stop here. In my next video, I will discuss this type of question again, because this type of question actually very important for any competitive exam, also for higher study. Also, I will discuss or more different method, reducible and irreducible test of polynomial. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.